Okay, here we look at another example of rational functions and everything that we have to do with them. So in this case, we have 2x squared on the top and an x on the bottom. So hopefully you can kind of predict in your mind, oh, since the degree on the top is bigger, the degree on the bottom is smaller, this is going to have an oblique asymptote. It's 1 degree off, so it's going to be a diagonal line. And that's kind of why we're doing this one too. All right, so first you might be asked to find the domain. Remember, the domain is just whatever makes the bottom 0. Doesn't even matter if it cancels with the top, so the domain is just that x such that x cannot equal -2. Okay, it's all numbers except -2. And therefore, we also have the vertical asymptote. Well, we think it's probably x equals -2, but I probably should try to factor the numerator and see if I can, and if something will like divide out with the x plus 2, right? So if I try to factor this, I get 2x and x because it's 2x squared, and then the 1 has to be 1 and 1, right? But that, to me, that does not seem like that is going to um, factor. Now, that won't add to 4 in any way. So no factoring. Okay, so we'll see what happens with the with that too. So our vertical asymptote then is x is equal to -2, and therefore our removable discontinuity, we have none. We removed nothing, so that is a none. Okay, our horizontal asymptote, right? If it's a larger degree on top and a smaller on the bottom, that's our oblique asymptote. So that is also a none. Okay. So therefore, we actually do have that oblique asymptote, and we have to find it. We can find it because it's going to be a line, and then we can graph it accurately. So in this case, remember, we're going to divide to find the oblique asymptote. And notice that the denominator is just x plus 2. So that means we can use synthetic division to divide because we can just put -2 on the shelf. You always put the 0 of that of the denominator on the shelf. Then we have a 2 here, a 4 here, and a -1 here. No missing terms. Okay, then we're going to do synthetic division. So we add. So bring down the 2 and then multiply and then add and then multiply and add. Remember that this is the remainder and we don't care about it. Okay, so our oblique asymptote here, then this is the 2x and this is plus 0. So it's just y is equal to 2x. Okay, so we'll graph the oblique asymptote and the vertical asymptote. All right, so before we do that though, I think we should go ahead and find the x-intercept and the y-intercept. Let's do the y-intercept first because I think that's easier. So the y-intercept, remember, is where x is equal to 0. So we're going to plug in 0 here, and we'll have a -1 on the top. And on the bottom, we'll plug in 0 here and just have a 2 on the bottom. So it's just -1/2. So in other words, the y-intercept is 0, comma, -1/2. Somehow I didn't label that, so I'll label it here. Y-intercept. Okay, the x-intercepts. Remember, it wasn't factorable? That means we need to use the quadratic formula to find it, okay? So the x-intercepts are where 2x squared plus 4x minus 1 is equal to 0. Remember where the numerator equals 0? Because the denominator would multiply by that 0 and we don't need to worry about it. So it's where the numerator equals 0. Okay, so to use the quadratic formula, we know that a is equal to 2, b is equal to 4, and c is equal to -1. Okay, so x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. I think I did that right as I was talking and doing it. So I got -4 plus or minus the square root, 16 plus 8, I think. So 24 over 4. You can simplify that. -4 plus or minus the square root. 24 is 4 times 6, right? So that would be 2 root 6 over 4. So x is equal to, that looks like we could divide by 4. We can divide by 4, so we would have -1 plus or minus, that 2 over 4 though is 1/2, so 1/2 root 6. Now, that's true, but really in this case, we really just want to know approximately what it is, right? So we just type that into our calculator and get 2 decimals, because otherwise, I mean, we need to be able to graph it. So the 2 values that I got were 0.22 and -2.22. Okay, so that should be good enough for us to graph. Okay, so let's take a look at this thing. We have a vertical asymptote at x is equal to -2, right there. And then we have an oblique asymptote that is y equals 2x. So remember when graphing lines, it would be mx plus b. The b being the y-intercept means the y-intercept there is 0. And then the line, the slope is 2. So that's up 2 over 1, up 2 over 1, etc. And then you can go back the other way, down to back 1. Okay. So remember to make the asymptotes a dashed line, because they are guidelines for the graph and they are not actually the graph themselves. If you graph them on your these functions on your calculator, you'll see they don't graph the asymptotes for you typically. You'll only see the actual graph. All right. We also have no removable discontinuity or horizontal asymptote, but we do have x and y intercepts. So 0, -1/2 is the y-intercept, and the x-intercept is 0.22, which makes sense there, and -2.22, which is on this side of the vertical asymptote. So actually, that's super helpful where the points are, because like, we can see where the graph goes. So at the end of the graph, it's going towards the slant asymptote. And then over on this side, in the middle, it goes down towards the vertical asymptote. Okay, over here, since we have a point over here, we know we're going up towards this vertical asymptote and then this direction towards the slant asymptote. Okay, so the final thing I think we should maybe do then on this graph is look at a few of the limits. Luckily, we didn't have to find any limits to be able to find the graph because we had the points there, right? So the limits around this vertical asymptote, this one up here would be the limit, let's see, it's f of x as x approaches -2. And over here, this is actually to the left, so the negative side of -2, and that is going up towards positive infinity. Okay. The other one is right here. It's for the vertical asymptote. It's going downwards towards -infinity, and that is the limit of f of x as x approaches -2 from the right, or the positive side, and that is going towards -infinity. All right. Then we also have our end behavior limits, and so those are, kind of strange as well. So this is the limit of f of x as x approaches infinity. Okay. So it is approaching infinity, that's true, but it is also approaching that line 2x. okay? And here it is also approaching the line 2x. And so that is our, that end behavior that it's doing. Oh, sorry, I wrote negative 2x because I was thinking negative infinity, but it's really, the graph is positive 2x. I just wasn't thinking. Okay, so 2x.